Okay, we reached to page 136 and the exercises number 18, 19, 20. But before I answer these questions, I want to look at this table which you have on the next page. Okay, so it's the summary of the Vesper theory for SL student. The SL student can use this table, and this table is very useful for them. When you draw the Lewis structure, then you can predict the shape of the molecule, electronic geometry, and the domain. So if in the Lewis structure there are two domains around the central atom, the electronic geometry would be linear. And usually when you have two domains, you don't have any lone pair there. So when the electronic geometry, when there is no lone pair, the molecular geometry and electron geometry are the same, and this is the shape of your molecule. Your molecule would be linear. As you can see in CO2, you have two domains here, one here, this is the second one, and the angle between these two domains is 180 degrees. In another situation, you may have three domains around the central atom. So when you have three domains around the central atom, the electronic geometry is trigonal planar or planar triangular. Okay, both of them are same. But there are two situations. In one of them, all of these domains are bound, and you don't have any lone pair on the central atom. So in that case, molecular geometry is same as electronic geometry. So molecular geometry is also trigonal planar or planar triangular, as you can see here in BF3. So in this case, the angle is 120 degrees. But another situation, when you have three domains, maybe one of the domains is the lone pair. So you have two bonds and one lone pair. In that case, your molecule becomes V-shaped or bent. This is an example of the V-shape or bent molecule. You can see your molecule is bent. It's like this, or it's like the V if you look at from the other side. And as we said, because we have the lone pair, and the repulsion between the lone pair and the bonding pairs are more than the repulsion which are available between the bonding pairs themselves, these angles become smaller, and from 120 degrees it decreases to around 170 degrees. Okay, it's approximately, so it is less than 120. And finally, when you have four domains, the electronic geometry is tetrahedral. There is a case that all of the four domains is bound, or all of the four domains are bound. So in that case, the molecular geometry or shape of the molecule is tetrahedral as well, which is drawn here. In that case, the angle between the bonds is 109.5 degrees. In another situation, three of the domains are bound and one of the domain is lone pair. In that case, your molecule becomes trigonal pyramidal, or we can say it's pyramidal. You can see here the domain which was here now is occupied by the lone pair, and the lone pair doesn't count in the shape of the molecule. So the molecule is like the pyramid, and the angle here decreases to 107 degrees, smaller than this one that you have here, because these lone pair exert greater repulsion force on these bonding pairs. And the last situation is that two of the domains are bound and two of the domains are lone pair. In that case, your molecule becomes V-shaped or bent, like in the water molecule. So in the water molecule, you have four domains. Two of the domains are lone pair, so the angle that you have here is even become smaller. It decreases to around 105 degrees. So you can see here two situations. You have the bent molecule or V-shape. One is here, the other one is here. The difference between them is their angle. If the electronic geometry is trigonal planar, in other words, if you have three domains, the angle is 117. If the electronic geometry is tetrahedral, or you have four domains, in that case the angle becomes 105. So this table you must know, and you only have these four domains for the SL student. So now let's go to the previous page. I will explain some point for you. The first thing which is important here, if they said why the angle decreases from 109.5 to 107 or to 105, you have to answer these as it's mentioned here. Is that the repulsion between the electron pairs varies as follows. So the strongest repulsion is between the lone pair, then lone pair bonding pair, then bonding pair and bonding pair. So if you have the lone pair, it causes the angle between the bonding pairs to become smaller because of the greater repulsion that you have here. Okay, it's also mentioned here, the repulsion. And what the Vesper theory says is mentioned here. Okay, so the definition of the Vesper theory is important. Is that, as its name suggests, this theory is based on the simple notion that because electron pairs in the same valence shell carry the same charge, they repel each other and so spread themselves as far apart as possible. So in these domains that we are talking about are electrons, and the electrons repel each other because they have same charge. So the best position for them is when they are as far as possible from each other to minimize their repulsion. Okay, so here some examples are given. In the previous videos we have talked about all of these examples that we have here. We have talked about BF3, we have talked about these molecules, we have talked about NO3 molecules, we have drawn the resonance structure for NO3 minus and so on. So we have talked about the ozone molecule, its angle decreases to 117 degrees, and tetrahedral, the angle is 109.5. but if you have one lone pair here, the angle decreases to 107. So if all of them are bound like here, the angle is 109.5 degrees. This is because the repulsion between these lone pairs and bonding pairs are more than repulsion that you have here between the bondings. And if you have two lone pairs, these two angles come closer to each other and becomes 105, like when you have in the water. Okay, so now let's go to page 136 and answer this question. Say predict the shape and the bond angle of the following molecules. H2S. Okay, so I want to find the shape of the molecule for H2S. The first step is to draw the Lewis structure. You have two hydrogens and one sulfur. In the periodic table you can see that the sulfur here is in group 16, so it has 6 valence electron, so plus 6, it becomes 8. Sulfur come to the center, single bond with hydrogen, single bond with hydrogen. You have to make it octet. This is become octet. Okay, so this is the correct Lewis structure for that. So let's find the domain for that. Oops, sorry. Okay, so the domain. So how many domains do we have? 1, 2, 3, 4. We have 4 domains around the central atom. 2 of them are bond, 2 of them are lone pair, so totally 4 domains. When you have 4 domains, the electronic geometry is tetrahedral. Okay, so here I use the abbreviation, but in the exam you have to write the complete name. Okay, so molecular geometry. So when you have 4 domains with 2 lone pairs, the molecular geometry becomes bent or V-shaped. So when you have 4 domains, this is the central atom. One domain is here on the screen, this domain is on the screen, this one is coming out, this one is going in, but 2 of these domains are lone pair. You can put the lone pair whenever you like, okay, but I put one domain here and one domain here, so the bent molecule is more clear in this case. So this is our molecule, and what would be the angle? The angle is 105 because it decreased to this angle. Okay, let's go to the next example. What was the next one? The next one is CF4. So let's draw the CF4. Total valence electron, carbon is 4 plus 4 times 7 for the fluorine. So totally we have 23 electrons. Carbon is at the center, single bond with 4 fluorines. Carbon is already octet. We only need to make the fluorine octet by putting the lone pair there. Okay, now how many domains do we have here? 4 domains, as you can see here. 1, 2, 3, 4. So the domain is 4. Electronic geometry and molecular geometry is the same because you have 4 bond and no lone pair. So in that case, both of them are tetrahedral. And when we want to draw the tetrahedral, one domain is on the screen, this domain is on the screen, this domain is coming out of the screen, or if you are writing on the paper, out of your paper, and these domains which is shaded goes into your paper. And here are fluorines, and the angle is 109.5 degrees. Okay, the next molecule is HCN. So let's draw the HCN. We have drawn this molecule before, but one more time I'll repeat it. You have 1 hydrogen, 4 carbons, 5 nitrogen. So totally you have 10 valence electron. So hydrogen, single bond carbon, single bond nitrogen. So the carbon is central atom. We draw the carbon, single bond with nitrogen, single bond with hydrogen. You have to make all of these atoms octet. So the carbon needs 2 lone pairs, nitrogen need 3 lone pairs. But when we count the electrons in this molecule, the number of electrons is 2, 4, 6, 8, 10, 12, 14. So we have 4 extra electrons. In that case, as I said, cancel the 4 electrons on the central atom, bring 4 electrons from adjacent atom between them. So the correct Lewis structure for this one is H, C, triple bond, N, and only 1 lone pair remains for the N. Now look at around the central atom. How many domains do we have? 1, 2. We have only 2 domains. So the domain around central atom is 2 bonds, no lone pairs, so you have 2 domains. So again, one more time, no matter if you have double bond, triple bond, or single bond, all of them accounts for 1 domain. Okay, so when the domain is 2, electronic geometry and molecular geometry are linear. So for the linear molecule, we have just draw the linear as it is in Lewis structure. And what would be the bond angle between these 2 bonds or these 2 domains? As you guess, it's 180. Okay, and let's go to the next molecule. The next molecule is NF3 that we have, then BCl3. Okay, for NF3, total valence electron, nitrogen is 5, plus 3 for fluorine, 7, becomes 26 electrons. Nitrogen come here. So I won't go to more details about the Lewis structures because we have drawn all of these examples before. Okay, so this is the Lewis structure. The domain around the nitrogen is 1, 2, 3, 4 domains. So the domain is 4, 3 of them is bond, 1 lone pair, it becomes 4. So when you have 4 domain, the electronic geometry is tetrahedral. You can look at the table that I have shown you in your book and determine the electronic geometry. And when you have 1 lone pair, in that case the molecular geometry would be pyramidal or trigonal pyramidal. So when you have 4 domains, as we said, these are 4 domains. Okay, so one of these domains are lone pair, so I delete this one, I put a lone pair here. The rest of the domains are fluorine. And what is the bond angle? Bond angle decreases from 109.5 to 107. Okay, so let's go to the next molecule that we have. What is the next molecule? BCl3, as I said. Okay, BCl3, total valence electron. Boron is in group 13, so it has 3 valence electron. Fluorine in group 7, so it has in group 17, it has 7 valence electron. So the total valence electron here is 24. So you have boron, single bond chlorine, single bond chlorine, single bond chlorine. You cannot make the boron octet because it has 3 electrons. If it shares 3 electrons, it can reach to the 6. It already has 1, 2, 3 bonds, which means it has 6 electrons. Okay, so it shares all of its 3 electrons here in the bond, so nothing remains for itself. But the chlorine, you have to make them octet. And if you count the electrons, there are 24. So this is the correct Lewis structure. So around the central atom, you have 1, 2, 3 domains there. So the domain is 3 bonds, no lone pair. Domain becomes 3. So when there is no lone pair, the molecular geometry and electronic geometries would be the same. And for 3 domains, there are trigonal, planar, or planar triangular, as it's mentioned in your book. Okay, so what is the shape of the molecule? It's like the Mercedes-Benz arm, like the logo of the Mercedes-Benz, like this. So the molecule is planar, so all of these bonds are on the screen, and the angle between them is 120 degrees. Let's go to the next molecule. The next molecule is NH2Cl and then OF2. Okay, NH2Cl, total valence electrons, nitrogen is 5, plus 2 for hydrogen, plus 7 for the chlorine, equal. Okay, so it becomes 14, yeah? One more time, 5 plus 2, 7, plus 7, 14 electrons. So you have 3 atoms, nitrogen, hydrogen, chlorine. Nitrogen comes to the center. Usually the atom which is written at the left side comes to the center. Okay? Or we can say the atom which needs more electron to become octet. Nitrogen has 5 electrons. It needs 3 electrons to become octet. Chlorine has 7 electrons. It needs only 1 electron to become octet. So nitrogen comes to the center. Okay, so the nitrogen forms single bond with 2 of the hydrogens and 1 of the chlorine. Then we have to make them octet. Nitrogen needs only 1 lone pair, chlorine needs 3 lone pair to become octet. And the number of the electrons that we have here is 14. 2, 4, 6, 8, 10, 12, 14. And the number of the domain around the central atom, around the nitrogen, you have 3 bonds and you have 1 lone pair, so it's 4. When it's 4, the electronic geometry is tetrahedral. But because you have 1 lone pair here, molecular geometry would be different from electronic geometry, and it is pyramidal. And when you want to draw, okay, you have 1 domain here at the top, 1 domain here, One domain is coming out of the board, one domain is going into the board or a screen. So I delete this domain and I put the lone pair here, chlorine, hydrogen, hydrogen. All of these three bonds are the same, so no matter where you put the hydrogens and when you put the chlorine. Oh, sorry for this problem that I have here. Okay, now what would be the angle? For the pyramidal structure, the angle is 170 degrees. This is the approximate angle, not exact angle. It's different from the molecule to molecule, and it depends on these atoms that you have here. Also these atoms. But it's less than 109.5, around 107. Okay, so let's go to the next molecule, which was OF2. I think we have drawn this one also in previous videos, but I'll do it here one more time. Oxygen is 6 plus 2 fluorines 2 times 7 becomes 24 electrons, or 22. 20 electrons becomes 20 electrons. Okay, so we have oxygen, single one with fluorine, single one with fluorine. We have to make all of them octet. Okay, this is octet for the fluorine, this is octet for the fluorine at the right. For the oxygen, it has 2, 4, 6, 8. And if you count the electrons here in this molecule, there are 20 electrons. So this is the correct Lewis structure. How many domains do we have around the central atom? 1, 2 bonds plus 2 lone pairs. So the domain is 2 plus 2, or 4. So that's why the electronic geometry becomes tetrahedral. But molecular geometry is different from electronic geometry because you have 2 lone pairs. In this case, when you have 2 lone pairs, the molecular geometry is bent or V-shaped. Okay? So you can just draw the molecule like this. F. It's like the water molecule. 2 lone pair here. And what would be the angle? 105 degrees. Okay, so if you want to be more precise, you have one domain here, one domain here, one domain here, one domain goes into the board. I can put fluorine here, and these 2 domains I can make them lone pair. This angle is 105 degrees. Okay, so we have done with the question 18. Question 19 is more challenging because drawing the Lewis structure is a little bit more challenging than the Lewis structure in question 18, but they are easy if you know the steps for the drawing Lewis structure and then for predicting electronic geometry and molecular geometry. It would be very easy. So in the next video we talk about the question 19 and 20.